Good afternoon. Honorable Director, sir, distinguished guest, honorable faculty members, scientists, and my dear students. It's a distinct privilege and a great honor that I have been invited to give this Professor Jyoti Prasad Medhi Memorial Lecture. I have heard many stories about Professor Medhi, but in my lifetime, I had never had a chance to meet him. He was a world-class scholar, a teacher of highest order, otherwise he would not have inspired so many of his students. Because as a teacher myself, I think that one of our responsibility or one of our qualities is to inspire our students. And I think Professor Medhi did it because I have heard so many stories about how he, as a teacher, inspired his students to do research, to learn, and to be good citizens of the country and the world. And now, listening to all the stories from Chaudhary sir, from Professor Das, I have come to know that he also was a great human being. And again, I thank Institute of Advanced Study in Science and Technology for inviting me to deliver this lecture. Specifically, I thank Dr. Gautam Chaudhary and also Professor Lavananda Chaudhary sir. So the title of my presentation is Econometrics and Time Series Analysis in Economics. By no means I can have the knowledge on stochastic processes or on time series that would represent Professor Medhi, and I am more on the applied side, so I apply time series techniques to address some of the questions that I ask in my research. Many years back, Professor Dale Jorgensen is an econometrician at Harvard University, and he teaches econometrics. Econometrics means he actually does pure theory econometrics. And as many of you probably have the same feeling about theory, sometimes we are not into theory. We don't really, it's very hard for us to sit through a lecture of 1 hour, 20 minutes or 3-hour lecture of theory, not necessarily in mathematical statistics or mathematics or physics, in any field. So, like many of us, his students at Harvard, they were also quite bored, and some of them were quite sleepy. So one student, he stood up and he said, but professor, what about the real life? Because theory is mostly abstract, and sometimes it is very difficult to relate theory to the real life. So he was asking this question just to kind of break the monotony probably. What about the real life? So Professor Jorgensen did not really stop. He continued lecturing, but he said, don't worry about real life. Real life is just a special case. So I am not going to talk about theory here in this lecture. I will talk more about the real life and how some of the theories from mathematical statistics or mathematics can be applied to economic theory. So the area of economics where we do mathematical modeling or we apply statistical techniques to economic data is known as econometrics. If I don't really mention econometrics, then probably my colleagues in my profession will not like it, and that's why I thought that it would be a good occasion, or it would be a good opportunity for me to say a few words about econometrics as well. So let's first think about what is econometrics. So this term, econometrics, is believed to be coined by an economist. His name was Ragnar Frisk, and Ragnar Frisk is from Norway. He was born in the end of the 19th century, and he actually was one of the recipients of the Swedish Riksbank award in memory of Alfred Nobel, which is also known as, or sometimes referred to as, the Nobel Prize in Economics. This did not actually, the money doesn't come from the trust of Alfred Nobel. So Ragnar Frisk is one of the first recipients of the Nobel Prize in Economics. So he coined the term econometrics. So what is econometrics? Econometrics, sometimes there is a misconception that econometrics is just applied statistics applied to economics, but it is not quite so. Econometrics is the unified field or unified study of economic models, mathematical statistics, and economic data. Of course, mathematical statistics is a big part of econometrics. Now, in econometrics, we make a distinction between two types of econometrics. One is econometric theory, and the other is applied econometrics. So in econometric theory, those who work, they develop or they try to develop various tools and methods, and they study the properties of those methods. And in applied econometrics, we try to develop quantitative economic models. Those are empirical models. And we use econometric techniques or econometric methods to economic data to answer some of the questions that we ask in economics. So, and if I have to classify myself, I will put myself in that, the last bullet point, which is applied econometrics. So I am more of an applied econometrician, and I know very little of econometrics, although in my student life I had great privilege to learn statistics or econometrics from people or from great teachers like Professor Jishnu Datta in Cotton College, Professor A.L. Nagar, Aniruddhalal Nagar at Delhi School of Economics, Professor K.L. Krishna at Delhi School of Economics, Professor Herman Behrens at Southern Methodist University, Professor Tom Pomby at Southern Methodist University, Professor Esfandiar Masumi at Southern Methodist University. Those are the great teachers that I had the opportunity to learn from. Although, again, if I think about theory, I know very little theory. I just try to apply some of the theory or some of the methods based on those theories to my research work. Now, when did or where did we in economics started using mathematical models? And that too, we started using probability models, or we can say the concept of stochastic processes are used in economics. When did we start that? It started with, again, a Norwegian economist or mathematician, you can say, Trisby Havelmo. In 1944, he published a paper in the journal Econometrica. And the title of the paper was The Probability Approach to Economics. And after that seminal paper, it is almost a kind of widely accepted approach in economics. So what he argued in his paper, 1944 paper, is that the economic phenomena cannot be explained by deterministic model. So these quantitative economic models must be probability models, because you cannot apply deterministic models to non-deterministic data. And that viewpoint and that argument was widely accepted in the field of economics. And after that, economists, the researchers have started using this widely, they have been widely using this probability approach in our quantitative models. Of course, there is a distinct evolution of this approach. So we call the structural approach, where we specify a model to explain certain things in the economy, and we say that the specification is correct or is fully specified. So those are the structure. That is the approach of the those who apply structural approach. But then that is not quite interesting, because some of the things that happen in the society, some of the things that happen in the economy cannot be correctly or appropriately specified through a mathematical model. Again, I mean, just to backtrack a little bit, at some point the economists realized that, like the physicists who argue that the phenomena that happen in the physical world can be written in the form of equation, at some point economists also started thinking that the phenomena that take place in the economy, this related to human behavior, can also be kind of expressed in terms of equation. And that's when we started moving more like the scientist, right? That's where we started using quantitative mathematical models to explain what happened or what goes on in the economy. So structural approach is closely related to this probability approach. And then the next evolution is the quasi-structural approach, where it says that model is not exactly specified. It is just an approximation of what happens in the economy. And then there is semi-parametric approach. So part of the phenomena we try to explain, and part we leave kind of open. So that is semi-parametric approach, which is what we extensively use nowadays. And then there is the calibration approach, where they basically don't believe in the structural approach. They said, well, most of the time the models are wrong, but then we can estimate, or we can kind of find some parameters looking at some just simple data or simple data. So that is the calibration approach. Normally there is a mathematical model, and then they try to calibrate to the real world. But these are kind of the approach which is kind of come under what we now know is the probability approach to economics. Now, when it comes to data that we use to answer economic questions, most of the data are observational. That also means that variables must be treated as random and possibly jointly determined. And therefore, it is very difficult to establish causality, what causes what, because there is less opportunity in economics to do experiments, because most of the economic questions or most of the economic issues are related to human behavior. Of course, nowadays, there is a new trend that we do a lot of experimental economics. So we actually have moved from the field, from history, to laboratory type settings. So sometimes we try to do we try to collect experimental data. But mostly in economics, they are historical data, observational data. They are not really experimental data. As a result, it is very difficult for us to change something and see the effect of that on something else. And so it is very difficult unless we have some very well established or well formulated theory. It is very difficult to establish this causal relationship between economic variables. So the data structure that normally we work with, of course, we work with cross-sectional data, and that is more prevalent in the field of microeconomics. Microeconomics deals with individual economic agents like producer, consumer, firms, right? And we normally apply or we normally gather cross-sectional data to study macroeconomic issues. Then there is time series data, which is what I will be talking about a little bit more. And time series data are mostly related to finance or to macroeconomics. Macroeconomics meaning when we look at the economy as a whole. So if we look at the Indian economy, those are macroeconomic phenomena or macroeconomic issues. Then there is a mixture of both cross-sectional and time series, and then we use panel data. And then there are cluster data, spatial data, spatially dispersed data. So those are kind of the data structure that we use to answer economic questions. Now let's kind of take a look at the time series, how we use time series in economics, and what are the things that we are interested in, and how we can apply time series techniques to economic data to answer the questions that we ask in economics. So generally when people talk about economic issues, and since I come from the macroeconomic, my specialization is in macro monetary economics. So I look at the big picture. So when we look at the big picture, what are the issues that we look at? Growth. For example, this is something that almost everyone talks about, even the politicians talk about growth. So when we talk about growth, economic growth, what do we exactly mean? It's growth of generally some measure, which is a measure of the overall performance of the economy. Generally, we use gross domestic product. That is the total value of all final goods and services produced in the economy. And the percentage change in that gross domestic product is essentially what we call growth. So when the Prime Minister says that India is growing at the rate of 7% or 8%, he's essentially talking about the growth rate of gross domestic product. Similarly, we talk about inflation. So inflation is an increase in the general price level. It is not about the increase in the price of a specific commodity or specific service, but it is the price of overall price of or average price of different goods and services which are regularly consumed by consumers, if we are talking about consumer price index, or it is wholesale price index if we are talking about the producer side prices. So the percentage change in that price index or the general price level is called inflation. Again, inflation is very, very important, particularly when we talk about consumer price inflation. Obviously, that affects our day-to-day life. If there is inflation, that means the value of money goes down. And when value of money goes down, of course, we are not very happy. So that is why we are concerned. There are other reasons why economists are worried about inflation, because inflation also affects the credit market. For example, if there is too much volatility in inflation, again, I'm introducing some of the concepts that we are interested in where we use time series techniques. So if there is too much volatility in inflation, what happens? It creates uncertainty in the economy. And when there is uncertainty in the economy, people do not borrow, people do not lend. And when that credit market doesn't work, investment doesn't take place. And if investment doesn't take place, then growth doesn't happen. So if we really want the economy to grow, then obviously we would like to reduce that uncertainty. Of course, some part of uncertainty we cannot do much about, but there is some part of uncertainty that we can control. We cannot entirely control, but we can have some control over. And inflation is something that not me, but the monetary authority or the government can do something about. And therefore, the central bank generally in all countries, they try to reduce the volatility or fluctuations in inflation so that that uncertainty gets reduced and the financial market or the market in general works properly. So that's why we are interested in inflation. Unemployment, of course, we are interested in unemployment. If a country and economy has high inflation, high unemployment, that also affects the labor market. That kind of represents the state of the labor market. So high inflation signifies that the labor market is not very good. And those who will be looking for a job in that market, it's very likely that they will not be able to get a good job very easily. And that is about unemployment. And unemployment has certain relationship with inflation and growth. Then stock prices. Nowadays, even in developing countries like ours, the financial market has been increasingly playing a bigger role. So earlier, financial institutions or financial system means only banks. Nowadays, financial system also includes the stock markets and stock prices. And some people are very much into the stock market and they regularly observe what is going on in the stock market. They look at the stock prices. For example, in India, we look at Sensex index, which is an average price of different stocks that are traded in Bombay Stock Exchange. So all these phenomena that we are interested in can be better understood when we kind of think of them in terms of changes over time. In fact, inflation, growth, those things are defined as changes over time. Or if we look at unemployment, which is not defined in terms of changes, or stock prices, those things also make sense only when we think in terms of changes over time. And that also gives us the clue why we would be interested in time series analysis of the economic data. The one particular thing or one characteristic of this time series in economics is that they are history dependent, meaning they depend on, let's say, if we look at the gross domestic product of India in the first quarter of, let's say, 2017, that also depends on the past value or lagged value of the gross domestic product. That means the gross domestic product of India in the first quarter of 2017 depends on, to some extent, the gross domestic product in the fourth quarter or third quarter or second quarter of 2016. So it is history dependent. Similarly, it is also dependent on expectations because the economic actors or economic agents make a lot of decisions based on what they expect from the economy in the future. So as a result, what comes out as a data point or an observation in a time series as a result of the decisions made by the consumers and the producers in the economy or the government in the economy, those decisions are based on the future expectations. And as a result, in economic time series, it is not only dependent on the past values, but it is also dependent on expected values. So this history dependence or this expectation dependence of the economic time series also kind of lead us to study the dynamic structure and the dynamic relationship between variables, and that's where we apply the time series techniques in economics. So here are some examples of economic time series. So the first graph is, this is India's gross domestic product at constant prices and current prices. Of course, we are more interested in constant prices because that also represents changes in the total quantity of goods and services produced in India. So that bar diagram, that represents the constant prices, and the blue one is the current prices. In the case of constant prices, the base year is 2005. That means all the values are, because in order to make it comparable, you have to convert everything into the single unit. Here, unit is 2005 prices, and that's how we can compare the quantities over time. If you look at the right-hand side, that is the growth rate. So when we calculate the growth rate of the gross domestic product at constant prices, you see something like that. And well, that trend line you just ignore for now. And of course, it has a longer time frame here. We have data from 51 to 12, but that is a much shorter one. So this is just the last part of this graph. We can look at the inflation rate. So this is inflation rate from 1961 all the way to 2011. So as you can see, this is change in consumer price index. So percentage change in consumer price index. So as you can see, again, there are different patterns that you can observe. Then here is the unemployment rate, but I would not be very comfortable using unemployment rate in India because half of our economy is in the informal sector, never get captured in the unemployment rate. And that's why this is not very reliable. Most of the time for developing countries, people normally do not use unemployment rate for any economic analysis. Then if you look at the interest rate, there are two interest rates, call money rate and the 1-year bank rates. So the red one is the bank rates, that is how much the bank will pay to the depositors, and the call rate that is for the short-term loans, that is the interest rate on short-term loans. And then here you will see the Sensex from 2000 all the way to 2014. So these are some of the examples that economists are interested in, and then they try to apply the time series techniques to study these variables. So why we are interested in analyzing the data? Well, of course, we try to understand, economics as a discipline, try to understand the economic phenomena. So that hopefully will improve economic decision making because anybody who took Economics 101 knows that economics is the study of how people make decisions in the face of scarcity. Our resources are scarce, our wants are unlimited, right? So we have to make decisions, and how people as producer or consumer, they make decision, or even the government has to make decision. So by understanding economic phenomena, we can improve the economic decision making. Then we also want to, because various stakeholders in the economy, they try to kind of see what is coming in the future. So they need to know, or they just want to know what would be, let's say, a utility company, a electricity company. Electricity company might be interested in knowing what would be the demand for electricity in next month or in 6 months from now, so that they can plan accordingly. Again, it comes to the resource allocation decision, right? So how much to produce, when to produce type of decision. And then this analysis is extensively used in economic policy making. Of course, in countries like ours, sometimes policy is not well informed, meaning that they are not made based on well-found research. They just somebody, all of a sudden in the morning, they think that, okay, they have to increase this or they have to do that, and they do that anyway without any analysis. But more advanced economies, normally a lot of research goes into economic policy making, and that's where there is a great use of this kind of analysis. So now let's come to the time series. And again, I don't have to really go over all of this, but I still kind of leave it as a teaser, so that I just explain what are the things we are generally interested in. There are micro issues as well. I just talked about a few macro issues because that is the area where I specialize, but there are a lot of interesting micro issues as well, which are at the firm level or at the consumer level or the consumer level. So there are a lot of different issues, but I normally, in my presentation, focus mostly on the macro issues. So here, what is time series? It is random variables measured over time. A sequence of observation on a variable taken at discrete interval in time, right? So I can represent a time series like that, y1, y2, yt. Those are the observations on the variable over those period of time. And this process, these observations are a finite sample from a time series stochastic process, because that goes back infinitely into the past and will continue to go forward in the future. So this is just a sample, right? This is just a finite sample. So here, each element is treated as a random variable with a probability distribution. Again, I will not go into too much into those representation and all this. So in economics, what we generally do, we model, because I just told you that most of the economic data are past dependent, or they are dependent on expectations. So whenever we look at an economic time series, we normally try to write it or model it as having two additive components. So one is yt, let's say that is the series we are interested in. That is, g is a function of the past values of y and past values of the error term. And error term, most of the time we assume it as a white noise process, right? Has a mean, zero mean, and a constant variance and a constant. I think it is Gaussian. Yeah, that's right. Yes. That's a Gaussian, yes. And then we have the error term. So what we essentially try to say that our focus is mainly on that g. We try to characterize that. And then et, which is the error term, is basically an innovation or a shock to the series at time t and assumed to be white noise. So that's the framework that we use to analyze economic time series. And then, well, of course, there are a lot of variations, and there are specific issues and problems that we try to address in our different methodology. Okay. So if we forecast that, so that's what happened. So that is based on the information. So it minus 1 is that is information available at time t minus 1, right? And then the forecast error is essentially that error term that I termed as innovation or the shock. So again, I already said all this. So whenever we use statistical technique, generally the time series techniques, our goal is to describe the function g, or we try to find the nature, or to try to figure out the nature of the function z that describes the part of y that is predictable based on past values. And also, and that is more relevant in macroeconomic and financial data, we try to describe the variance of the innovation ET, how volatile or how variable that innovation is from the past. But that, again, sometimes that's where we really fail to do a good job. Most common specification, and that's again a time series analysis 101, is a linear stochastic process where function g is linear and the number of lag values of y and epsilon appearing in g is finite, right? So here is a representation of ARMA, autoregressive moving average of order P and Q. So the autoregressive part has an order of P. That means we go back to the Pth lag, and Q is the moving average lag. That is, in the moving average, we go back to Q. So that is kind of the very basic time series analysis normally we do with the economic time series. And one concept that is very important in economic time series analysis is that of stationarity. So again, even we sometimes use a little bit different terms, which is not generally used by statistician or mathematician. So the stationarity is essentially what? It is a process. A process is stationary if a time series following that process has the same probability distribution at every point in time. Okay? So the effects of any shock must eventually die out as the shock recedes into the infinite past. So what essentially happens, we try to also understand the economic phenomena using general equilibrium, what we call the general equilibrium model. So generally in general equilibrium model, we try to derive some steady state. That is kind of the sustainable path of the economy, and I'm talking about macroeconomics. And in the economy, of course, you cannot totally control, and so there will be shocks, and that shock might come from technology, that shock might come from war, that shock might come from tsunami, that shock might come from a stock market crash, or that shock might come from some scandal with our prime minister or president, right? So that shock can come. So, but once that shock comes, that shock will, of course, disturb various economic measures, but eventually it should come back to the steady state. If we cannot characterize the economic time series that way, then of course there will be we'll have to think about something else. So that's where the stationarity, the concept of stationarity is very, very important. Now I will skip this because here I had a little bit more formal and more in-depth kind of stuff from that stationarity part, but then I'll leave it here. Now, so we do a lot of univariate time series analysis of the economic time series, just to characterize that series, to know, and then again, when we do that, we break it into two parts, one which is predictable, the other is not predictable. And then we try to characterize that predictable part so that we can use it for forecasting. And of course, unpredictable part, which is totally random, which is of course is not possible for us. So we do a lot of univariate kind of analysis where we just focus on one variable. But again, economists are storytellers. So as a result, that is sometimes not very interesting, or sometimes we try to go beyond that when we look at multivariate models where there is more than one variables, and we try to look at interrelationship between variables. So in the multivariate analysis, there are some techniques that have been used over the years. One technique is called the intervention analysis. That is basically a simple regression model where you have a dependent variable, you have independent variable, and then there you introduce some sort of shock or intervention, and then try to see what happens to the dependent variable. But again, since we use observational data, the problem or the challenge is that it is very difficult to, of course, in intervention analysis, since this is an exogenous shock, it is relatively easy, but when it comes to the other independent variable, which we model in the model, in particular regression model, it is very difficult to establish the causality. And sometimes the models are not fully specified. And nowadays, there is a moral hazard problem. Nowadays, well, of course, we have computers software. And as a result, once in a while, we'll find papers which are submitted to professional journals. And sometimes these researchers, so-called researchers, they send papers where they probably don't know what exactly they are doing. But the good thing about the computers is that you just input the data and then it will spit out some outputs and then they report it. And I have had papers coming from relatively good journals, which sometimes this researchers writes that, oh, I did not do this because Stata or because SPSS doesn't have that subroutine. But that cannot be an excuse, right? So that is our kind of moral hazard problem. Without knowing, they try to model or they try to estimate things or they try to apply statistical tools to economic data. And now, in purely empirical work, specification, of course, is a major issue. Most of the time, the models are not well specified. And that's why intervention analysis, a lot of researchers, they do it, but in many cases what happens, they do not kind of appropriately specify the model. Then there is transfer function analysis. Again, the same thing, you will have to identify a dependent variable and independent variable. Unless your empirical specification is informed by a very strong mathematical model, theoretical model, structural model, then of course there is a high probability that your model is misspecified, particularly when you rely entirely on observational data. And in many economic phenomena, what happens is there is a feedback mechanism, and it happens a lot in macroeconomic data. For example, gross domestic product may affect employment, employment may affect gross domestic product, or gross domestic product may affect stock prices may affect gross domestic product. So there are a lot of we call reverse causality, right? So, or feedback mechanism, and it is very difficult to capture those kind of feedback mechanism or reverse causality in intervention analysis and transfer function model. And therefore, the economists came up with this idea of this is actually, I think, obviously, the clue or the hint or the initial came from statistics, but then I think it was independently developed in the field of econometrics, what we call the vector autoregression. It's an econometric model used to capture the linear interdependencies among multiple time series. Now, here so we are basically looking at a simple system of two equations. Of course, this is a vector autoregression of order 1, right? You can have a vector autoregression of order p. So I can write it as a vector, and then I can also write it as a matrix, and that's why it's called vector. It's basically an extension of autoregressive model. Okay? And then from there are concepts of Granger causality. Clive Granger, he won the Nobel Prize in 2002 in economics, and he was one of the initiator or proponent of the vector autoregression model. So, and he introduced this concept of Granger causality. Granger causality is not causality in the sense of causality, it is temporal causality. So, if something happens today, if something else happens tomorrow, then if there is a statistically significant link, that we call the Granger causality. For example, if investment takes place today, obviously that investment will have an impact with a time lag, right? So in that case, we will call that is a Granger causality or temporal causality. So it's not the causality in the general sense of causality. Then in order to kind of examine the interrelation, we also look at something called impulse response analysis. So if you give a shock to the system, so what happens to different variables that we are interested in? Along the same line, we can also have from the same framework, we can have variance decomposition. Those are the things that kind of gives you an idea. For example, of all the variation in gross domestic product, how much of it is caused by the labor market, how much of it is caused by, let's say, a capital investment. So those kind of things we can kind of extract from both impulse response analysis and variance decomposition. So I'm coming to almost my last slide here. So there are challenges in time series modeling. So when we try to, of course, we have neat methods and theories, but when it comes to applying those theories or models or methods to the economic time series, we have certain challenges, and some people have been working on it. For example, data vintaging is an issue. So what happens with the economic data? Generally, the government agencies will announce, let's say, gross domestic product data today. Okay, so if they announce or they publish the data today, generally they put it like preliminary, or they will say first estimate. And after a few months or a year, you will see that the data has been revised. But then when they announce the data today, that has some repercussions in the economy because people react to that, right? So now when we try to analyze an economic phenomenon, so which data do we rely on? Do we rely on real-time data, which we call in econometrics, we call it real-time data, meaning the data that they are publishing today. Whether it is preliminary, first estimate, doesn't matter. That is the real-time data, because looking at that data, people will react, the market will react, right? And then after 3 months or after 6 months, they can revise it, but then that data is already old. So the data vintaging is a specific issue which kind of is sometimes troublesome, and as a result, there are now a new line of research in macroeconomics who actually use real-time data rather than the revised data. Then there is systematic sampling. So you can think of, let's say, GDP is a continuous variable, but we observe data at discrete time points, right? So that is a systematic sampling problem, right? So, but there might be important information in those time periods where we did not collect data or we did not observe the variables. So that kind of leads to some of the problems. And then temporal aggregation. Many of the data that the government agencies or private agencies publish is an aggregation of observations or time, or the data that are observed in different points of time. For example, when they talk about annual data, so it might be an average of monthly data that have been collected over 12 months period, right? But that what happens as a result? It smooths out, right? But then a lot of important information may be lost in that process. So that is one issue that we have to be aware of, at least those who do time series. Then fitting deterministic time trends. So most of the time what happens, people look at the data, and that happens a lot with people who writes in the newspaper or who writes for popular press, and then people generally read them and then they react or they do their own analysis. But fitting, sometimes the trend may not be exactly a linear trend, it may be a non-linear trend, or what kind of trend that we choose. So how do we choose those kind of things, or how do we fit a trend in economic data? Those are important issues which a careful time series econometrician or time series person will, applied time series person will pay attention to. And then when we look at the economic data, particularly macroeconomic data or financial data, we see structural change or structural break, because economy, the structure of the economy changes over time. But if you mechanically apply time series techniques or mechanically apply statistical techniques, what might happen that you are actually not making a distinction between structural break and short-run shocks, transitory shocks, right? Because when you talk about structural breaks or structural change, it is generally understood, at least theoretically, conceptually, as something which is permanent, right? And it may build up over a period of time. So determining or identifying those structural breaks could be a very, very difficult task. So that's a challenging thing. So those are some of the challenges that as an applied time series econometrician or time series person face when they try to apply the time series methods or techniques to economic data. I'm done. So if you have any question, I'll be happy to take those questions. But again, thank you for giving me this opportunity to speak in front of you. And I am also thankful because this is a very special occasion. One of the greatest mathematician and statistician from our part of the world. It is his birthday, and I'm really honored to be here and to speak to you on whatever little I know about applying time series to economic data. Thank you very much.